Okay, this is a quick video on scope, free variables, bound variables, and closed and open formulas. Okay, so the idea of scope and binding in predicate logic is the same as in syntax. So if you've taken 322, you know what scope is, you know what binding is, you can bring that here. If you don't know what it is, don't worry, we'll talk about it now. Okay, so if we have something like all x px, I'm going to use a very simple tree first to talk about this. We know that we can break this up into components. So all x px, and then px breaks into p and x. If we have square brackets and all x is essentially like part of it, so all x is outside the brackets, everything inside the brackets here is called its scope. So all x scopes over everything inside those square brackets. So all x scopes over px. So a formal way of saying it is if x is a variable and alpha is a woof to which a quantifier has been attached to produce all x alpha or exists in x alpha. So in other words, we're taking a well-formed formula, we're attaching a quantifier to it, then we say that alpha is in the scope of that quantifier. So basically, everything inside the brackets is in the scope of that quantifier. Another way of thinking about this is that everything in the syntactic tree that the quantifier C commands is in the scope. Now, what does C command mean? Well, let me explain C command with a picture. So we look at the quantifier. So we're going to say all x C commands something. This is just a tree relation. And how C command works is it takes a look at its sisters. If it has more than one sister, it takes a look at all of its sisters. And it C commands everything in the sister and all of its daughters and granddaughters and great-granddaughters. So it takes a look at its sister and everything below it, and that's what it C commands. So we say that all x C commands px. And this is the same thing that's saying all x C commands, or all x scopes over everything in px, or px is in the scope of for all x. So C commands is how we determine scope. So for example, in the one that I have written out on the right here, the one that I've typed, we see a formula, exists in x, mjx, and for all y, py. So we can break this up into components. Exists in x, mjx, we can tell by the brackets where this scopes over, and for all y, py. So if we want to know what exists in x scopes over, we can just check everything inside the brackets there. So exists in x scopes over mjx, or we can use C command. We can say, okay, here's the quantifier in our tree. Let's look at its sisters. Let's take its sister and all of its daughters, granddaughters, and so on. Everything it dominates, and that is what is in the scope. So we can say mjx is in the scope of the existential. Okay, same with for all y p of y on the right. Well, we can take a look inside the brackets to see what it scopes over. So py is in the scope of for all y, or we can do the C command trick, all y, py, okay. There it is. That's its sister and everything below it. What I want to do, actually, in this example, is I want to look back at the question we did in the last video. And specifically, I want to take a look at this question right here. We're talking about scope. So for all x1, what does for all x1 scope over? Well, all x1 scopes over everything inside this bracket. So it scopes over for all x2, px1, x2, and j equals b. And we can check this using C command. So we can highlight the thing, we can highlight the quantifier, and we can say, okay, it scopes over its sister and all of the things that it dominates. So for all x1 scopes over all of that is in this little black box. We can do the same thing and we can ask about x2. So let's do this in orange, why not? Okay, what does all x2 scope over? Well, everything inside these brackets, and we can check with C command as well. It checks its sister and everything the sister dominates. So all x2 scopes over px1, x2, and j equals b. Okay, so this is how scope works. So in this question, you should determine the scope of each of the quantifiers. If you want, you can draw a syntactic tree. I'm just going to look inside the brackets because it's a little faster. But if you want to draw the tree, you can prove to yourself that ccommand still works. So for all x, what does all x scope over? Well, the bracket starts here, and we follow this bracket until it ends. And where does it end? This is a great question. It looks as if it has no ending because the question was not written out completely correctly. Okay, well, good thing this is a video. So I'm going to end it there, and I will correct it in the slides for when we do the live lecture. So it ends here. So we can say that the scope of for all x is going to be exists a y, lxy, and py. So that's the scope of for all x. Now, for the existential with the y, what's the scope of that? Well, we just check the inside of the brackets. So it starts here, and it goes and goes and goes until it hits our closing bracket here. So the scope of exists a y just consists of lxy and py. Finally, let's do our existential with z. What does this scope over? Well, the bracket starts here, and it goes and goes until it closes over here on the right. So we say that the scope of the existential with z is going to be pz and ljz. Okay, the predicate, not the wrapper. Anyways, that would be how we can determine scope. And if you do a syntactic tree for this, you will find that thing ccommand, and you can determine scope that way. All right. So the last big thing is really free and bound variables. So basically, a variable can either be free or it can be bound by some quantifier. If a variable is bound, that means it is in the scope of the existential or the universal. So for example, let's take a look at this tree. For all x exists a y, pxy, or exists a z, kz, kxz, and ky. Okay, we can break this up, and I see for all x here. So what is the scope of for all x? Well, we take a look at its sister and everything that that sister dominates. So this is the scope of for all x. So every variable x that is in the scope here is bound. So the x in pxy is bound, and the x in kxz is bound. Okay, let's try exists a y. Let's do this one in green. So we check. Its sister and everything its sister dominates is in the scope of the existential for y. So this y is bound in pxy, and that's the only y that we have here in this part. Now, if we take a look over on the right, on this side ky, there's a y over here, but this y is not in the scope of the existential on the left. As you can see, it's not being c-commanded. And if we take a look at the brackets, the square brackets, ky is outside of those brackets. So we call this a free variable. So in translation, this would be a pronoun, like it or she or he or they or whatever. Whatever pronoun you choose. That is determined specifically by the person who is translating the sentence or by the sentence you are trying to translate. But just an arbitrary case like this, it could be literally any pronoun. But that's called a free variable because it's outside of the scope. Let's take a look at the last quantifier that we have here, the exists as z. So we take a look here. Everything in its scope is what its c commands. So its c commands kxz. Well, z is in here, so z is also another bound variable. So this has 4 bound variables and 1 free variable, and we determine that by scope. Now, one thing I want to make clear is that if we have something like exists as z such that p, let me use the square brackets for this, p, z, and then we have, say, a proper name like Kate here, only the z here will be bound, and Kate is neither free nor bound. This is just a constant. Constants do not have a free or bound status because they are people in the world. Variables, x, y, z, which we'll use for variables in this course, or w or u, those can be free or bound because they change depending on what happens to them. It's a variable. We don't know what it is. Okay, so that's free and bound variables. The last thing to talk about are open and closed formulas. So a formula is called closed if there's no free variables. Basically, this means there's no variables at all, or all the variables are bound. So, for example, exists a y, sleeps y. This is closed because y is bound. Y is bound by the existential, and this could be translated as something sleeps. So there is some y such that y sleeps. Marries Jim Carroll. This is also closed because there's no free variables. This could be translated as Jim the subject marries Carroll the object. Here's something a little bit more complicated. All x, all y, all z exists a w. Loves xy and marries yz. Well, x is bound by for all x, y is bound by for all y is bound by for all y, and z is bound by for all z. So this is closed. There's no free variables. Even though we have this exists a w, w doesn't show up, so we just ignore it. Like, we don't have to account for things that are bound, so we can have exists a p in there, and there's no p in there, it doesn't matter, it's still closed. So this could be translated as everything loves and marries everything. It's a little bit weird of a translation, so if that doesn't make perfect sense in English, that's okay, because it's a really weird way of saying that. If we had an actual translation for this, it would look a little bit different, probably. Okay, the last one, a little bit more complicated, but this is still closed. Exists in X such that king X, so something is a king, and for all Y, if Y is a king, then X is equal to Y. So here we have this X is bound by the existential, and this Y is bound by the universal. So everything is bound here. These are closed. And this sentence would translate to the king exists. I don't think we'll talk about how we translate the, but this is sort of the strategy for it. If it looks scary to you, it kind of is. Anyways, we'll talk about this again when we do translation. I don't expect you to understand all of these translations right away. If you are getting them right now, fantastic. If not, it's fine. Okay, if a formula has at least one free variable, it is called open. So tall x, x is free. It's not being bound by anything. So this would be a pronoun in translation. So it, x is tall. So something, well, I shouldn't say something is tall. I should say x is tall. But x is a variable. It's free. It converts to a pronoun. Exists a y such that x is slim. Well, x is free. There's nothing binding x. Well, there's an exists y out there, but there's nothing with y in there, so we just ignore it. So there would be x is slim. It is slim. For all z, x assassinates z. Well, x is free again. We don't know what x is. Z is bound. This is fine. But we have at least one free variable. So this is an open formula. So we could translate this as it assassinates everything. Because for all z is everything, every z. So some x, or it x, a particular x, assassinates everything. Finally, for all y, puppy y, and cute y. So this y is bound by the universal. Everything is a puppy. But this y over here, cute y, this is outside of the scope. As you can see, the brackets only scope over everything in puppy y. So this y is free. So this is an open formula. So we really have two sentences here. We have everything is a puppy, for all y is a puppy, and y is cute. But y here isn't bound, so this is a pronoun. Everything is a puppy, and it is cute. Anyways, that was it for open and closed formula. Next week, we're going to start by talking about translations and predicate logic, do all the predicate logic stuff, and then we'll switch over to scope ambiguity. So next week will be a full lecture. The week after that, when we do scope ambiguity, it'll be a really short lecture. I'm going to give you basically a little mini reading break that week. So we're only going to do about an hour of lecture, and you'll have 2 hours to study for the test, catch up, just take a little bit of a mental break from everything going on, from learning new things. And yeah, that'll be the trajectory for the next 2 weeks. If you have any questions, as always, discussion board, email, I'll get to you when I can.